right, we're going to look at a couple of problems where we're using one of the special limits that we've looked at to evaluate the limit. So the relevant limit that we already talked about for this problem is one that we proved using some triangles and sandwich theorem. So we looked at that in another video, why this limit is what it is. But at this point, this is just one you should memorize. And this limit is 1. It's important to remember when you do that the theta needs to be in radians. And this is not one that you can do by just plugging in the value for the variable. Obviously, the denominator would be 0. So this is one that you have to prove using some theorems. Once we've proved it, though, you can just memorize it and then use it in some other problems. All right, so one of the things that you might notice is that I have a very similar problem over here to what this theorem is, except I have an extra 7 in this problem. So what we want to talk about in this example is how do I deal with that extra 7. And I intentionally use different variables here in the problem that we're working on and the theorem that we've got here. So the key thing with this theorem is that this expression here needs to be the same. So whatever the expression is inside the sine function, that needs to be the same as the expression on the denominator. And then that expression needs to be approaching 0. All right, so if we look at this problem here, one thing that we might notice is I have a 7x in here, and I really wish I had a 7 down here on the denominator of the fraction, and then it would all match up like that. All right, so then we can think a little bit about algebraically. Could I just put a 7 there? And the answer is yes, you can just put a 7 there as long as you're doing it in a way that's algebraically valid. So I can multiply by 7 on the denominator of this fraction, as long as I also multiply by 7 on the numerator of the fraction. So I put it at the end there, but that's 7 times the entire numerator. So I've really just multiplied by a form of 1. The reason I did that and the way I kind of arranged it the way I did is that here on this side we have this sine of theta. In this case, our theta is 7x all over theta. And so I've got that kind of grouped here. So that is that special limit form. All right, here we have x approaching 0, but we know that when x approaches 0, 7x will also approach 0. Numbers very close to 0 for x. Even when I multiply them by 7, they will still be approaching 0. So I don't need to put a 7 there, but I just need to ensure that when x is approaching 0, this expression that I have here would also be approaching 0. All right, so I've kind of grouped it like that, and now we can use this special limit to just evaluate. This part here is going to approach 1. So that's 1 for this special limit. Over here. And then I still have this out here, so we don't want to forget that. So all of this part I have here in parentheses is approaching 1. And then that whole thing is going to be times the 7 that's there. So we'll go ahead and finish that. So 1 times 7 is 7. So that's the answer for this limit. All right, it's always a good idea when you're using theorems to go ahead and check your answer to make sure that it makes sense numerically or graphically. So something you might do is just get out a calculator and plug in some numbers that are really close to 0. And you should check to see that you're getting outputs that are really close to 7. You want to make sure you're in radian mode. And you want to make sure that the expression is the original expression typed in correctly, plugging in numbers very close to 0. And you should see that you get numbers very close to 7 when you do that. All right, we're going to look at one more problem that's just a little bit more complicated here. So let's see. We're going to do the limit as x approaches 0 of 2 times tangent of 3x all over sine of 4x. Okay, so if we're going to be using this special limit to do that kind of problem, one of the things that we want to think about is where are these expressions that would be like a sine of theta over theta in this problem. All right, so I'm going to do a little bit of rearranging. One thing that you should remember is that tangent is sine over cosine. So there's a sine function here in the tangent function. I don't want to forget about the cosine function that's on the denominator, though. So I'm going to kind of do like I sort of did in the previous example, where I kind of just pull this apart a little bit and think about the parts so that we can get this special limit form in different parts of the expression here. Okay, so I should write this limit out front. We should always write that out front until we've actually evaluated the limit. This 2, I'm going to kind of just pull off to the side here. And I'm going to use parentheses to kind of regroup some things here. The tangent of 3x is sine of 3x over cosine of 3x. So the sine of 3x, I'm going to want to kind of get this sort of form here. So I'm going to put that in one parentheses. We'll just put that all over 1. And then the cosine of 3x, though, I'm going to pull that apart from here. Okay, so here's my tangent of 3x, sine of 3x over cosine of 3x. I pulled those apart, though, because really what I'm looking for with this special limit is this kind of form here. All right, so I've got the 2. I've represented the tangent of 3x. I also have this sine of 4x that's on the denominator. So I could put all of this over sine of 4x, but then I have fractions within fractions. So an easier way to write that would be to just write that as times 1 over sine of 4x. Okay, so some parts of what I have here are easy enough to evaluate the limit of. As x approaches 0, 2 approaches 2. It stays 2. As x approaches 0, cosine of 3x will approach cosine of 0, which is 1. So this part here with the 1 over cosine of 3x is also easy to evaluate. These two expressions here with the sine of 3x and the sine of 4x, these are what I'm going to try to get to look like this, so I can use this special limit to evaluate the limit of the overall expression. Okay, so sort of like in the previous problem where I wanted there to be a 7. So I just put a 7 there, but then I had to think about the algebra to balance that out so that I'm not changing the original expression. I want to do the same thing here. So if we look at this sine of 3x, I would really like there to be a 3x on the denominator. So I'm going to multiply by 3x on the denominator so that there's a 3x there. So I have this kind of expression. But I can't just do that without balancing it. So I need to also multiply by a 3x on the numerator. I'm going to go ahead and multiply by a 3x on a numerator out here. I'm going to start a new group here. And I'm just going to leave the denominator blank for a second there. So here's my 3x. I wanted this here so I could get this special limit form. And then the 3x that I have here is really just to balance what I did here. All right, and then I want to do the same thing here with this sine of 4x. I'll do that in a different color so we can kind of emphasize where everything went. But this sine of 4x, I would really like this to be 4x over sine of 4x, which would be actually the reciprocal of this relationship. And then I can use a reciprocal thing to rewrite that part. But I would really like this to be 4x over sine of 4x. So I'm going to multiply by a 4x here on the numerator. And I can do that as long as I balance that. So multiplying on the numerator to balance that, I would multiply by 4x on the denominator. So this is what I wanted. And then this 4x that I have here is what I needed to balance what I did to get what I wanted. Okay, so at this point, I could write out one more step, or possibly I could think about just evaluating this limit as it is. I'm going to go ahead and write out one more step this one time, but it's OK if you kind of combine some steps and are able to evaluate the limit from here. All right, so I'm going to just change some of these things. So I have the limit as x approaches 0 of the 2. I'm going to leave alone. The sine of 3x over 3x, I'm going to leave alone. That is my special limit form. The 1 over cosine of 3x, I'm going to leave alone. I mentioned something about this being the reciprocal. So technically, this limit here is 1. So technically, I would need to use a theorem about combining functions. I can really write this fraction as 1 over the reciprocal of this fraction. And then you can see that you really do have that special limit form. It's here on the denominator of this fraction. So that looks kind of messy. This is maybe the step I said maybe want to write this out or maybe not. But that kind of makes it clear where this limit fits into this problem. All right, and then I need to not forget this part here that I added on. So I have 3x over 4x. Notice that this part here actually does simplify some. So this 3x over 4x, whether I do it now or in a separate step, I actually could go ahead and just reduce that to 3/4. I multiplied by those x's for two different reasons: to balance one of my special limit forms and then to balance the other special limit form. But then I can go ahead and cancel them once I've got everything set up to balance out. Okay, at this point we should be able to go ahead and evaluate this limit. So as x approaches 0, 2 approaches 2. This is our special limit form. So this part here approaches 1. 1 over cosine of 3x. I said that out loud, but didn't write anything down at the beginning of the video. As x approaches 0, cosine of 3x will approach cosine of 0, which is 1. So this fraction here approaches 1 over 1, which is 1. This here, where I've got 1 over that special limit form, will also be 1 over 1, which is just 1, and then times the 3/4 here at the end. All right, so when I multiply that all out, 2 times 1 times 1 times 1 times 3/4, I get 6/4 or 3/2. All right, so you should be saying, I should want to check that, and that's a good idea. You should check that. You should plug in some numbers really close to 0 into the original function. Make sure you're in radian mode, and you should notice that you're getting values, decimal values, that are very close to 3/2 or 1.5. All right, try some more problems like this, and hopefully you can get through no matter how complicated they are, no matter how many parentheses there are. You just got to keep track of balancing everything.